Lecture problem 7. A 2,000 kilogram trolley is pulled up a 30-degree hill at a constant velocity of 30 kilometers per hour by a winch at the top of the hill. How much power is the winch providing? As you must know by now, the best way to solve these questions is by setting up a free body diagram. The winch is providing the power by acting on the trolley by means of the tension T in the string, and that tension is pointing up the incline. This is the tension T. The other two forces are the normal force and the mg. The normal force is acting perpendicular to the surface of contact. This force is known as the normal force. The mg is acting straight down. The system coordinate is going to be chosen in such a way the x-axis is lined up with the direction of motion, which is up the inclined plane. Notice that the angle that the mg makes with the y-axis is the same as the inclined angle, which is 30 degrees. Based on this system coordinate, the only force that needs to be broken into components is the mg, and those two components are negative mg cosine the angle theta along the y-axis, and also negative mg sine theta along the x-axis. Remember that this angle theta is the inclined angle, which equals to 30 degrees. Now that we have prepared the free body diagram properly, let's move on to the mathematical derivations. The power that is going to be provided by the winch is defined as the work done by the winch through the tension divided by the time t. So the work done by the tension is the same as the work done by the winch. So the only thing that you need to work on is the work done by the tension, and there are two different ways to do that. You can find the work done by the tension using the equation that has been introduced for constant forces. The work done by the tension, therefore, is going to equal the tension, which is a constant force, times the displacement d, times the angle that is made between the tension and the displacement, and that is equal to 0. The displacement is that one that is parallel to the x-axis. Notice that cosine 0 equals to positive 1. The next thing that you need to do is to evaluate the tension T using the dynamics of Newton's laws. The sum of the forces acting on the system of interest, which is the trolley, equals the mass times acceleration. There are three forces acting on the trolley, which are the tension, the normal force, and the mg. All of them equal the mass times the acceleration. Along the x component, we have a positive tension T. We have no normal force because the normal force is lined up with the y-axis only. And the mg has a negative mg sine theta component along the x. Notice that the acceleration is 0 because the question stated that the trolley is pulled at constant velocity. Therefore, the ma is going to equal 0. This x component alone is enough for us to figure out the tension. Isolating the tension T, you obtain mg sine the angle theta. Remember that this angle theta is the inclined angle, which equals to 30 degrees. You can work on the y component if you want, but that's not necessary at all. The y component will lead to the following. The tension is lined up along the x, therefore it doesn't have a y component. The Fn has a positive component equal Fn, and the mg has a component equal negative mg cosine theta. That's all you need to do with the y component, and the only thing you can get out of it is the normal force equals mg cosine theta. Now let's substitute the tension that we have obtained into our work equation. Therefore, the work done by the tension is going to equal, instead of the tension, I am going to write down mg sine theta times the displacement d. Cosine 0 is equal to positive 1. The other approach that can be used to solve for the work done by the tension is the following. the work done by the non-conservative forces equal the change in kinetic energy plus the change in potential energy. The work done by the non-conservative forces include the work done by the tension and the work done by the normal force. Those equal the change in kinetic energy plus the change in potential energy. However, the change in kinetic energy is going to equal 0 because the trolley is being pulled at constant velocity. The KE final must equal the KE initial. The delta PE is going to equal MGH final minus MGH initial. The reference point of measurements for the heights is going to be chosen the bottom of the incline. Therefore, the H initial is going to be 0. The height final is going to be the top of the incline. Because of that, the initial potential energy MGHI is going to equal 0. Also, the work done by the normal force is 0 because the normal force is perpendicular to the displacement, which is up the incline. The remaining quantity that needs to be evaluated is the height final, and that can be done using the trigonometry of this right triangle. Notice that the sine of the angle theta, which is my 30 degree, equals the opposite, which is the height final, divided by the hypotenuse, which is the displacement d. Isolating the h final, you obtain d sine theta. Substituting the h final in our work done by the tension expression, we obtain mg. Instead of the h final, we have d sine theta. Notice that this expression that I have obtained for the work done by the tension is exactly the same as the expression that I have obtained earlier using the first method. Choose whichever method you want, the result is going to be the same. Now that we have established the relationship for the work done by the tension, we can find the power. We use the work done by the tension divided by the time t. The work done by the tension is mg d sine theta, which is the inclined angle, divided by the time t. Notice that the ratio of the displacement over time is known as the average velocity. The average velocity equals the magnitude of the displacement divided by the time t. Making the substitution, we obtain the power to equal mg instead of d over t, that's the average velocity, times the sine of the angle theta. One important information that we need to be aware of is to convert the velocity that is given in kilometers per hour to meters per second. After you do that, substitute for the mass, the gravity, the velocity, and the angle theta. You can solve for the power to equal 82,000 watts.